Welcome to another WebGL Playground Tool tutorial. In this video, I'll talk about building our first 3D model, which will be a cube. We'll do it in a nice and simple way, and then afterwards we'll utilize some utility functions that come out of the box with the tool so we can make our code a little bit cleaner. So when we talk about building a cube is just 6 sides, and each of those sides is an identical square. And we can kind of define that cube by 8 vertices, and I'll label those vertices A through H. And the set of vertices that are on the screen right now are some nice unit vertices, so that each x, y, and z is just the value 1 or negative 1. And I alternate about negatives and positives to get all of the desired vertices that we show in the photo here. So I'll hide my camera real quick, and you'll get a good look at each of the sides. And so imagine just looking at these sides straight on and matching up the labels you see here to the vertices in the model from the prior slide. And you'll see here that we want to color each of these a different color. And if you ever need to refer to the vertices that I'm drawing, just come back to this slide. So the drawing order is important, like we always talk about, and for each side I've listed out the drawing order that I want to have for each face, and I've also listed out the color that I want to have for each face. And so whenever I'm drawing things, I'm just going to be referring to these for our first go around. So let me pull up the tool here, and we'll start drawing some of these sides. So I'm going to go to the Vertices tab, and I'm going to define 4 vertices, A, B, C, and D. That'll make sense in a second here. So A, I'm going back to slide 3 of the presentation. A is all 1s. B is a 1, negative 1 for Y, 1 for Z. C is negative 1 for X, negative 1 for Y, 1 for Z. Lastly, D is negative 1 for X, 1 for Y, 1 for Z. And the vertices E, F, G, and H directly mirror A through D, except each of the vertices negates the Z value. So E, F, G, and H can go here. Then we'll go ahead and negate each of those Z values. Now if we move back to the drawing orders slide, I'm going to just go ahead and push these vertices onto my vertices array, and we're going to do 6 sets of 6 pushes. I'm going ahead and copy this and paste it 5 more times. 1, 2, 3, 4, 5. And I'm just going to start filling these in like the drawing order slide says to do. So A, D, B, A, D, C, E, A, B, E, B, F, then E, F, G, E, G, H, then D, H, G, D, G, C, capital D, then E, H, D, E, D, A, then F, B, C, F, C, G. So those are all of our vertices. So we'll go over to the Colors tab and define the colors that we want to use. And the code I'll write is going to be sufficient for all of the code, or all of the vertex code that we'll write for the rest of this video. So I'm going to write a function, push color, and that function is going to take a color and the amount of times we want to push that color onto the colors array. So we'll just declare a loop here. And we'll go ahead and say colors.push color I times, or count times in this sense. So we'll go ahead and define our colors. So I'm going to say colors and counts is an array of JavaScript objects, and each of those objects is going to have a color, which is a vertex, and a count value. Now for the sake of this video, all the counts are going to be 6, so I really don't need to code that in there, but if you were using this for more complex code, it would be nice to be able to define our counts in a way like this. So the first side is red, the second side is green, third side is blue, the fourth side is the yellow side, the fifth side will be purple, and the sixth side will be cyan. And then we're just going to iterate over this colors and counts and push, we're going to go for each on these colors and counts, and these are all, each index represents a JavaScript object. So I'm just going to call it JSO, and we're going to call the function we defined on the color of each JSO and count of each JSO. So if I did everything correctly, when we load this in, we actually shouldn't see anything, and that's because our object is living right on the brink of the view volume. If we rotate, you will see it a little bit, but we'll pause here, and we're going to go back to the slides to talk about the utility functions and how we can make this code a little bit nicer. Move that over. Okay. So the utility functions are designed to kind of help you modify your vertices in a nice way. What we just did back there is a little bit impractical. We had to write 36 lines of code to push 36 vertices into the vertices array, which isn't exactly ideal, and we want to be able to do this programmatically. So the functions that I've provided out of the box with this tool are rotate X, rotate Y, rotate Z, translate, and scale, and these will all help us achieve that goal. So all the rotation functions take 2 arguments. The first is the vertex we want to rotate, and the second is the angle that we want to rotate it by. Now, a vertex has to be a vector, xyz with a w of 1, and all of the angles that we're using for these rotation functions will be in radians. Just as a reminder, to rotate completely about an axis, that's just like rotating in one circle, so that would be 2 pi radians for one full rotation. Now these functions, like I said, are rotate X, rotate Y, and rotate Z, and each function takes a vertex and then returns a vertex after the rotation is complete. So I've drawn a little graphic on the side to kind of demonstrate how rotations go, but if it's not making sense, or if it's not clear, you can use the right hand rule to help visualize that in front of you. So all you have to do is point your thumb in the direction of the vertex that you want to rotate about. So if I was doing Y, for example, I would point my thumb up, and the way that my fingers go towards the palm of my hand is the way positive rotation works for that axis. Negative rotation would just be, in essence, flipping your thumb around. I'll show an example of this later in the video, so if that's confusing, just sit tight. The next function that I want to talk about is the scale function, and we can use the scale function to take a vertex and 3 arguments that will modify those vertices, alpha, beta, gamma, and those correspond to x, y, and z respectively. So this function will go ahead and take the alpha, beta, gamma and multiply them by each x, y, and z, and it will apply that multiplicative factor to the vertex that we pass to this function. So for example, if we pass all of the vertices one by one into this function for the square on the right hand side of the screen, and give each vertex an alpha, beta, gamma of 0.25, then every vertex's x, y, and z will be scaled down to 1/4 of its original value, and we'll get that smaller square that lays in the middle. Lastly, is the translate function, and the translate function is really nice. If we apply it to every vertex in a model, it will pick up that model and put it somewhere else. And this function takes 4 values, a vertex, and 3 what we'll call delta values that we will use to modify the vertex that we passed in. So if we want to move, for example, the triangle on the right-hand side of the screen down and to the right, for every vertex in the triangle, we'll apply the translate function to give it a positive x and a negative y value. So let's move back to the playground, and we'll play with each of these functions to kind of see how they work. So I will drag this over. And so the first function that we're going to want to deal with so we can get this shape that we've defined inside the view volume and see it is going to be the scale function. So we're going to take all of our vertices and map that vertices array, to where each vertex is scaled down by a quarter of its original size. So we can use map, which takes a given value, or takes all values in the array we're applying it to, and does an operation on them and replaces them. So we can say vertices.map, and we take for each vertex v, we're going to apply the scale function on that vertex with a 0.25 value for each x, y, and z. So that'll take every value and multiply them by 0.25 in the x, y, and z. So if we go ahead and load it, we'll see that shape is much smaller, but it's within our view volume, so we can see it. So if we see a rotation here, we'll see it spin around, and that's the model that we defined with the given colors. So the next shape that we're going to talk about, the next function we'll talk about is the rotate function, and we'll start with rotate y. And we'll lead into this by kind of talking about what we're going to do. So each side of this cube is the same, so we really only need to start with one side and then move that side around using the rotation functions to all of the places that we want to move to. So we'll define that first side by the same method of pushing that we've done here. So that would be A, C, B, then A, D, C, and we can draw that first side by just pushing everything from the first side array, which we can use with the 3-dot or spread operator. And now if we delete these, we will see the same shape. We'll still see that red side, and we haven't touched any of the other sides yet. So if we want to get rid of these 6 lines of code, we can do a rotation about y this time. And since we're going to be rotating the red side to the right for the green side, using the right hand rule, I see that that is a positive rotation about the y-axis. So what I'll do is I'll push onto the vertices array everything from the mapping of the first side to a rotation about y, and since we're rotating a quarter of the way around the cube, that is a quarter of 2 pi, or math.pi over 2. And then now we can get rid of these 6 vertices that we've defined here. If we give it a load, we'll see that nothing really changes, and as we come around to that side, we'll see that green side. So let's go ahead and do that for the next side, which would be the backhand side, or the blue side. So we'll take our first side and do a map on it, where we map each vertex v to a rotation about y, and this time we're rotating twice as much as we did for the prior side, so we only have to rotate about math.pi this time. Now we can get rid of the vertices that we defined and go ahead and load. What we see here is the blue side is still there, and this mapping went ahead and removed those 6 lines of code that we deleted. Next we'll do the yellow side, which was the left side, and we'll map the first side for every vertex. We'll do a rotation about y, but this time, instead of going all the way around 3 pi over 2, we don't need to do that. We can just do the negative version of what we did for the right-hand side. We'll do a rotate y for each vertex, negative math.pi over 2, and we can delete the 6 vertices that describe that green side. We do a load here. Shape stays the same. As we come around to the left side, we see it's green. Next is the top side. Now we're no longer rotating about y, but if we're taking a side and either moving it down or we're moving it up, this rotation happens around the x-axis. So let's say vertices.push. We'll spread our first side and map it. And since we're going to rotate about x, we'll use the rotate x function. Now let's think about by what angle. So if we are looking at this shape in the front and want to move it to the top, if we were to go ahead and point our finger in the x direction and curl our fingers, we would see that a positive rotation would actually be bringing that side to the bottom. So we actually want to do a negative rotation here, and this is again a quarter rotation about the x-axis. We'll do a negative math.pi over 2, and we can get rid of those 6 vertices that define that side. Go ahead and load. As we rotate, we'll see the purple side stay there. Lastly, we can do the same exact process for the bottom side, but except we are going to rotate positively. Delete that negative, delete those vertices, and now if we go ahead and load and rotate, once the bottom side comes around, we'll see that nice cyan color on the bottom. So that was rotate x and rotate y. So let's remember real quick, the cube goes purple on the top, and then green, and then cyan, then yellow. So to demonstrate the rotate z function, what we'll do is we will do a vertices dot push, where we reassign all the vertices, but we're going to rotate them positively around the z-axis. So what that should do is if you hold your finger out and curl your fingers into your palm, you'll see that we're going to take the shape and move it about the z-axis. And since it's centered, all it's going to do is just spin it in place. So we'll do a vertices.map. We'll take each vertex v, and we're going to apply a rotate z to it. Now if we do this positively, we should see the green side go up to where purple is. Purple should go down to yellow. Yellow should go to cyan, and cyan should go back to the green side. So let's do a rotate z, and we'll just do it positive by a quarter. And we do a load here. We see that the red's still in the front, but now green is on top, purple is on the left, cyan is on the right, and yellow is on the bottom. Lastly, to demonstrate the translation function, we'll do vertices equal vertices.map, and we'll take each vertex and let's translate it up to the right by 0.5 in the x and 0.5 in the y. So we'll say vertices.map v translate each vertex. We're going to add 0.5 to the x, add 0.5 to the y, and we're not going to touch the z. And if we go ahead and do this, we should see that shape move up to the right. And when we begin rotation, the shape is no longer centered, but I'm rotating about this whole shape about the axis 1, 1, 1. That's x, y, z, 1, 1, 1. So what we'll see is we'll kind of see it spin. The whole shape will start to spin around that. And as it starts to spin, this very corner will leave the view volume. That's why you see that kind of cutting of that one edge. And then when it comes back in, you see it again. So that was a little demonstration of all of the utility functions that I mentioned in the PowerPoint. I'll take this code, And I will go ahead and put it in the templates tab here so you can access this and not have to go through the video and write it again from scratch. And yeah, if you missed the first or the second video, I will link them both in the description so you can kind of get a sequential or chronological view as to how we've been approaching these problems. And yeah, thanks for tuning in. I'll be doing more of these in the future. And